Hi, this is Group 1, and for Project 3, we conducted the material selection for internal combustion engines connecting rods. So what is a connecting rod, first off? They're most commonly used with internal combustion engines and steam engines. It converts the reciprocating motion from the combustion from the piston into the crankshaft and into the wheels as work. The connecting rod is required to transmit the compressive and tensile forces from the piston, as it cannot fail in everyday use. For this analysis, we examined a connecting rod from a Nissan Altima, Sentra, and Rogue engine of a 2.5-liter four-cylinder engine. This engine's a inline four-cylinder engine that utilizes gasoline and is still in production today. We have some information up there, and we can see that from the analysis that we're going to be doing that we can actually model this pretty well. For this analysis, we need to assume a constant square cross section. We can do this because of the areas that we are focusing on. We want to focus on the highest likelihood areas of buckling and failure, which is the thinnest section of the connecting rod. We are assuming a width of 22.75 millimeters and a length of 143 millimeters. We're going to assume a maximum RPM of 7,000, which results in a maximum compression of 35 megapascals. This is a low capacity engine, and so we don't need a very high RPM margin. And we want to have a stress ratio of -1 to have the worst case fatigue analysis, so that way we know that this piston will survive in all cases. And we wanted an expected service temperature range of -40 to 185 degrees Celsius. 185 degrees Celsius is the expected operation temperature for a normal internal combustion engine, and then -40 degrees for when the engine is stopped and it's in its starting warm-up phases, especially in places like Alaska and Canada.
So how do we go about choosing the right material? So the first thing we're going to do is go ahead and eliminate as much materials as possible by applying a 15 megapascal per meter squared limit for the fracture toughness. Doing this leaves us with a total of about 31 materials, mostly metals and a few composites. So the first translation we're going to go through is with regards to the compression loading. Here the function being that the rod must withstand those loads from the compression of the piston firing. The constraints being, as specified before, of the geometric limits. It must be stiff enough to resist 0.1 millimeters of elongation or compression and 35 megapascals of pressure. Objective here is to minimize the mass and choose the correct material and width of the cross-section to do so. Going through the material index derivation for the compressive loading, we first use the stiffness, use that equation to plug it into the mass, and find the material index to be the Young's modulus over the density. Plotting a line of this material index on an Ashby diagram, we can see that we've eliminated many materials, with our remaining materials being carbon steels, alloy steels, nickel-based superalloys, aluminum alloys, magnesium alloys, and our two composites, aluminum silicon carbide composites and CFRP. Going ahead and tabulating these materials with their Young's modulus and density, we find the material indices, and we see that first the best materials are CFRP, aluminum silicon carbide composites, and magnesium alloys. Moving forward, we're going to go ahead and do a buckling analysis. So we need to make sure that this rod does not fail due to buckling. Again, the constraints are the same as before with those geometric limits and the 35 megapascals of pressure. Once again, minimizing the mass and choosing the right material. Going through this material index derivation, we're going to go ahead and use the equation for buckling using the critical force with N equals 1 because of those loading constraints. We then find the material index to be the square root of the Young's modulus over the density. Plotting this line on an Ashby diagram, we see that we have essentially the same materials remaining with a few additions, one of the composites being GFRP and two metals, titanium and cast iron. Plotting or going ahead and tabulating these materials with their Young's modulus and density. Once again, CFRP and magnesium alloys do the best with the highest material index. but we've gone ahead and highlighted titanium and low alloy steels because they're not doing terrible. They're actually doing good, and we can see from other cases that these are the materials that are generally used.
So in regards to fracture and fatigue, we considered a fail-safe design for the rotting compression. As for our constraints, it was a similar constraints that were used prior. However, our objective now was to maximize the crack size before failure since our component cannot reach the failure. And as for the free variables, similarly as before, material and the width of the cross-section. So for the derivation, we went ahead and calculated for the endurance limit, which is the endurance limit over the density that gives us our fracture to mass profile. And after plotting this on Granta, we went ahead and saw that it was similar materials that we have listed prior to this. However, the one thing with this is that our component, the cycles here shown is 10 to the 7th, and our component, and that's very low for our component, which would have to be like up to 10 to the 9th. So if we go to the next slide, we'll be able to calculate for the fracture toughness, which is the fracture toughness over the yield strength. And here we still have the similar materials that were listed before. However, now we separated the low alloy steel and the low carbon steel and analyzed those separately. Once all the data from Granta was consolidated onto this table, we're able to see that the low carbon steel and the low alloy steels had the better performance compared to the rest in regards to also comparing it to the maximum crack size allowed. Titanium alloys also were an acceptable performance. However, we know that titanium alloys are way too expensive. And in order to get the crack size, we use an integrated version of the Paris law. And the crack size will be able to represent our surface roughness that would be used on our piston.
But with all of this considered, we also need to move forward and consider our surface temperature limits, which here on the left, we can see our minimum surface temperature limit of -40°C is ultimately our high carbon steel and e-carbon steel are not performing very well and should really be eliminated. And furthermore, on our high surface temperature scale, the wrought magnesium alloy would likely fail in the operations of the engine, or in the worst case scenario of, say, hanging out in Death Valley with your vehicle, you would exceed that maximum surface temperature limit with wrought magnesium alloys. So with that, we also now need to consider what processing and manufacturing methods we would use to make this connecting rod. We considered 3 methods, being die casting, hot powder pressing, and forging. Die casting being characterized by its very high capital cost, but very low unit cost at large batch sizes. Of course, it would also not require excess machining for the given tolerance limits that we determined previously with our fracture analysis. Furthermore, with hot powder pressing, this would provide good densification and more controllable material properties, but again, requiring extra machining with moderate capital costs, but not necessarily lower unit costs compared to die casting at excessively large batch sizes. And then finally, with regards to forging, this would require the most post-processing in terms of machining and heat treatment. However, it would have the lowest introductory costs, but would not necessarily be advantageous with very, very large batch sizes. However, ultimately, we do choose forging, as our analysis tended to conclude that at around a batch size of about 10,000 units, which correlates to 2,500 vehicles, which is moderate for this type of component, is forging would actually be a somewhat relevant, cheaper option, even with regards to the post-processing and heat treatment methods that would be required for the part to be operable and usable. So ultimately, this leads us to that, well, in terms of pure performance with regards to minimizing the mass for the most efficient engine, we would generally prefer titanium alloys. However, if we consider the extremely long lifetimes and lowering the material costs and manufacturing costs for sale of this vehicle that this would likely be in, we must prefer the low alloy steels with the higher density to endurance limit ratios. So with that in mind, we would in the future like to individually select the specific steel alloy, as well as numerically evaluate the final width given a desired component lifetime, which could vary with future evaluation.